Okay, how's everybody doing today? Doing good. We're almost done with the week. So a few items. One of major importance coming up on Monday. We're having a test. Okay, but I want to emphasize all the material from this current lesson, the dot products, these style word problems, the vector projections, none of that's going to be on the exam. Okay, I will give you the homework today. It'll be due on Tuesday, like we talked about, but none of this will be on there. What you're going to want to look at for the exam, really look to the quiz. Okay, those kind of operations with vectors will be on there. Magnitude, what was that formula? The square root of a squared plus b squared. Unit vectors, how do we find a unit vector? Okay, so Satish says v over magnitude of v. Absolutely right. Now, there's another formula that's very, very useful. If you know both the magnitude and the angle of rotation, you can immediately find the component form. You guys remember magnitude cosine theta, comma, magnitude sine of theta? That will definitely be on there because it's about half algebra, like the quiz, half word problems, okay, like we were doing immediately after that first lesson, vectors in the plane. Okay, so if you have any questions, please come on in. I'll still be here tomorrow morning. At least that's the plan as of right now. Excuse me. So come on in if you do need anything or you need a little bit of review on something. Um, Tuesday, we're going to do the homework. Like I said, we'll also probably talk about the test. I'm not going to see you on Wednesday due to the SAT. Okay, we're going to be taking that in the morning. So Thursday, I believe I mentioned this yesterday. I was going to go ahead and plan and begin sequences of arithmetic and geometric series, but we need to go ahead and take that T-test exam. That's when the math department has decided we'll go ahead and do that. So there is a little bit of good news. The other two classes have completely finished up the notes today, so that means that tomorrow you should have the entire period to go ahead and work on your assignment that I'll give you today. Okay, so you can ask questions, work together, all that good stuff. So that'll be happening tomorrow. That's all I've got, unless anybody has any other questions. Okay, then let's go ahead and get to it. Now, what we spent the majority of our time on yesterday were these incline problems, and I also went ahead and showed you a work problem. How many people had the opportunity to go home last night and figure out how many pounds of force it would take for both Mary and her sled to not go down the hill? Okay. So, Connor, what did you get? That's exactly right. So here's that problem I was referring to. So there's the diagram that we were talking about yesterday. Remember, the one nice key feature of this is that whatever the angle of incline is, this angle is always going to be the exact same measure. Okay. And then we just set up a simple trig equation. 108.3 pounds of force should keep that little girl and her sled from going down the hill. Okay, and then we started talking about some work problems. Now, work was pretty easy to find. You simply go ahead and take the component form of the force vector and you multiply it by the component form of the distance vector. Okay, so how many people had the opportunity to go home and see how much work the gentleman pushing the car did? The other word problem. No? Yes. Okay. So we simply take the dot product of the force vector and the distance vector, okay, as shown here. And this gentleman would have performed 848.5 joules of energy, or work, I should say. Okay. Anybody go home and get that one? Okay. All right, now remember, these word problems, this style won't be on the test Monday, but you will have those like we looked at in the previous week, where you would go ahead and add the two vectors together to get your resultant, and then you could go ahead and find the magnitude and the resulting angle rotation. Okay, so good. Well, what do I want to go ahead and talk about today? I'd like to spend the majority of our time talking about vector projection onto another. So what we say is the projection of u onto v. Those are typically the two vectors that we go ahead and use. Okay. Skylar, do you have any notes? Yep. Okay. So we write it like this. The projection of u onto v. So one of these vectors is going to be a subscript. Whichever one is the subscript, that's the one that's being projected onto. So I would read this as u onto v. So if I were to give you something like this, how would you read it? The projection of B onto A, because A is the subscript, it's the one being projected onto. Okay, and we kind of talked about this yesterday. You remember how we had those two components, W1 and W2, and I kept saying, which one is always parallel? We said W1, and W2 was always perpendicular. Okay, well, that's what's talked about right here in this paragraph. So let's see what it says. What if you want to decompose a vector into the sum of two vectors where u plus v equals the resultant? And if we did, how could we find those component parts? Let u and v be non-zero vectors such that u is equal to w1 plus w2. Now, when you use this formula right here, the projection of one vector onto another, this is what you're finding. W1. That is the vector that's parallel to the vector being projected onto. Now, give me a few minutes, probably about 5 minutes, because as I go through this, the first part is going to be really confusing. Once we get to an example, I'm hoping that that'll make things a little more clear. Okay, we know that W1 and W2 are orthogonal. As we said yesterday, that's perpendicular. Again, W1 is parallel to V. The vectors W1 and W2 are called vector components of U. The vector W1 is the projection of U onto V and is denoted by this right here. And here's the formula. Very simple formula. You're going to take the dot product of the two vectors, divide that by the squared magnitude of V, and then multiply that by vector V. So this formula will result in a vector. It's going to be a component form. Okay, so let's look at this in two ways. Before we go ahead and start looking at it algebraically, let's go ahead and look at it graphically. Okay, here are two examples. So in each, you're already given W1, the vector projection that we're going to be looking for, right? But how are we to know that that's where the vector is supposed to be? There's actually a really simple trick to figuring this out. We're projecting onto V, right? Pretend that V is the ground. Okay, you want to go ahead and place the sun so that the U vector is between the ground V and the sun, and the vector we're looking for, W1, it's the shadow that the sun would cast. So like this one here, pretend that V is the ground. Okay, so you might have to, rotate your paper, kind of tilt your head, but if I were to put the sun directly overhead, and it's shown straight down, well, the shadow that U casts, that's the projection vector we're looking for. That's W1. Okay. Now, connecting that to U, it's always going to be perpendicular. That's that W2 component that we're going to be looking for as well. Okay. Now, you'll notice over here, the angle theta between U and V, it's going to be obtuse, right? So while you'll notice the shadow, it may not be exactly on the vector V that you're projecting it onto, but it's still going to be parallel to it. Okay, so if I were to put the sun like right here, and it's shown straight down, here's U's shadow, the shadow of U. That's the vector projection that we're looking for. Okay, now connecting that shadow to U, perpendicular, there's your W2. Okay. So let's practice a few that haven't already been done for us. I didn't go ahead and bother making copies of these. We'll just go ahead and look at these together. Okay, and you can revisit these if you like. But for all of these, we're going to project U onto V. So basically, if I go ahead and put the sun in the appropriate place, where's the shadow going to be? Where is that vector projection W1 that I'm looking for? Okay, so let's say this one right here. I want to project U onto V. Now remember, V represents the ground, right? And I always want to put vector U between the sun and the ground. So for this first one, I would probably put the sun right here so that he shines straight down. Okay, well, his shadow would be right there. That's the vector projection W1 that we would want to find. Okay. Now, I've already done it. If I go ahead and connect that terminal to U, that's the other component W2 I'm looking for. Okay. So now you guys tell me on the next diagram, okay, U and V in that position. We have an acute angle. Where should I place the sun? Above, below, left, right? What do you think? We're still projecting U onto V for all of these. Okay, so Christian says it's going to be on the bottom. So if I were to put the sun here, yes, see, we want vector U between the ground and the sun, right? So the sun is going to shine its rays. Well, this would be the shadow. That's the vector projection W1 that we want. Now, if I go ahead and connect W1 perpendicular to U, that's the W2 that I'm looking for. Okay, the other component. Now, these two vectors don't even have to be connected in order to do this. Take a look at the third diagram right here. So I've got vector U, I've got vector V, and once again, I want to project U onto V. So where should I place the sun? Above, below, left, right? I put it on the left. Okay, very good. So if I put the sun here and he shines, well, then the shadow cast is probably going to look like this. That's the projected vector I'm looking for, W1. Okay. Now this one is the only one that's kind of different. I would then go ahead and connect this vector to the other one perpendicular, but neither one of these would actually represent W2, the other one. In order to get W2, I would want to go ahead and take V and move him over so that both U and V are touching. Okay, as the two sides of the triangle as they are in the previous diagrams. So for this one, we don't initially see W2. All right. Well, what about this one right here? We have an obtuse angle. Where should I place the sun? Above, below, left, right? What do you think? So it should still be above. In fact, you'll notice where I place the sun on this second diagram, isn't it in the perfect place for this one? So if I were to go ahead and shine down, where's the shadow going to be? Will it be on V itself this time? No. So it's still going to be parallel to it, but this is where the shadow would be. Okay, so that would be W1. Now if I connected that perpendicular to U, that's W2. Okay. So that formula that I just talked about a moment ago, it's going to give me the component form of that shadow that we're looking for. Okay, so how's everybody doing so far? Like I said, it's kind of different. It might take a little bit for you to wrap your head around this. I remember the first time I was taught it, I was completely lost. Okay, so it'll take a little bit of practice. All right. Let's come back over here. Let's look at it another way. Okay, so we've looked at it graphically. Let's do this. Excuse me. Let's say we have U and V. Okay. Now, you guys remember how in the first lesson, we would take the two vectors, we'd go ahead and put a terminal to an initial, and we use the triangle method to go ahead and figure out what the third side would be. So let's say that this third side right here, okay, let's say this represents U plus V. Okay, what did we call that? We called it the resultant. Okay, this is the resultant, yes. Okay, so we started with two vectors, which we used, we added them up, and we were able to get the resultant, right? Well, what we're doing now is the vector we're giving, we're pretending that he is the resultant. So we're working backwards to find the other two sides of the triangle. But here the two sides are going to be very specific. They're the two vectors that will be perpendicular to each other. Okay, so let's say what we're going to be doing with the vector projection. Okay, if I wanted to go ahead and project U onto V, let's say this is U, this is V. So think about what we were doing algebraically. If I project U onto V, that means I want to take U and figure out what his orthogonal components are going to be. So the sun would be right here. Here's the shadow. Here's the perpendicular one. So this would be W1. This would be W2. This is what the formula will give me. Okay. So this time we're starting with the resultant and we're working backwards to get the two component forms. But the components are going to be orthogonal. We're looking for the two that will create the right triangle. Is that starting to make a little more sense? Okay. Let's try an example. Let's see what you guys think. Okay. So example 6. Find the vector component for u equals 2, 3, orthogonal to v equals 5, 1, given that W1, the projection of u onto v, is 5 halves, 1 half. See, they've already provided me the component form of that shadow. Now, we haven't ever seen the formula in use yet, so let's actually go ahead and see if that's what we should get. Let's actually go ahead and find W1 and kind of confirm this. So W1, the projection of u onto v, first we take the dot product, then we divide that by the magnitude of v squared, and then we multiply that by vector v. Okay. So first let's find the dot product of u and v. How do I multiply two vectors? There you go. So I'm going to multiply the a's, so 2 times 5, that'll give me 10. Now I'm going to multiply the b's, so 3 times 1. And what do I do with those products? Add them up. So would everybody agree that the dot product is 13? Okay. Now let's find the magnitude squared. Okay, but here's where the square is going to play a really important part. The magnitude, as you guys told me at the beginning, is always the square root of a squared plus b squared, right? But what happens if I square that formula? There you go. The radical disappears. The squared magnitude is just a squared plus b squared. It's going to be the same as if I took v and multiplied it against himself. Okay, but let's go with this. So I need a squared, so that would be 5 squared, plus b squared, well that's 1 squared, and that's going to give me 26. Everybody okay? Okay. So finding those two parts right there, that is the majority of your vector projection formula. Okay, so now I'm going to go ahead and put the dot product, 13, over the squared magnitude, 26. Now all I have to do is multiply it by the vector, which is 5, 1. Okay. So do you notice anything about 13, 26 then? It will simplify to 1 half. So if I take 1 half and multiply it against 5, 1, what do I get? 5 halves and then 1 half. Wasn't that exactly what they told me the vector projection was? So see, that's all it takes. It's a very simple formula, right? Okay. But now let's tie this into everything I was talking about since the beginning of the lesson. You'll notice I've already plotted vectors u and v. U is 2, 3. So you'll notice I went 2 to the right and then 3 up. So this is u. And then vector v, 5 to the right, 1 up. So this is v. Okay. Now think about what we were talking about a moment ago. I want to project u onto v, meaning I want to find that shadow. That's what the formula is going to give me, the component form of that shadow, right? Okay, well here, where would I place the sun if the ground is v? Yeah, it'd be above, maybe a little bit over to the left. Okay. So let's say I place the sun right here. Well, the shadow cast is going to look just like that, right? Remember, that's W1. Okay. Well, look at the component form. Start at the origin. What is 5 halves as a decimal? 2.5. 1 half as a decimal would be 0.5, right? We'll go from the initial to the terminal of that shadow. Are we actually going 2.5 right and then 0.5 up? That's what the formula is giving me. The projection formula will give me the component form of that shadow. Is it starting to make a little more sense now? Okay. Well, where's W2? There you go. If I now go ahead and connect the terminal end of the shadow, that projection, to U, that's perpendicular, that's W2. That's actually what the problem is wanting me to find. So we haven't actually done anything in the problem yet to answer the question. I'm just kind of really emphasizing what we're talking about today. All right. Does anybody have any questions on what a vector projection is? Okay. Well, now that we know that that is correct, the problem is actually wanting me to figure out, well, what's the component form of W2? Okay. Well, if I know the original one, okay, remember this is the resultant, I'm going to break him apart into what we call W1. Remember, he's the shadow, he's the parallel one, he's the projection vector, plus W2, he's the perpendicular one. So he's the parallel, he's the perpendicular. Excuse me. So all I need to do is just plug in those that I have. I know U is 2, 3. We were provided that the projection vector W1 was 5 halves, 1 half. In fact, we found that ourselves, plus W2. And we've actually seen something very similar to this in the first lesson. We just need to go ahead and figure out what W2 is. So let's see, I can actually subtract that component form over. So I can say 2, 3 minus 5 halves, 1 half equals W2. Okay. Now, what is 2 minus 5 halves? Okay, negative 1 half. And what is 3 minus 1 half? 5 halves. So this should be the component form of that W2 vector that I wrote right there, the one that's perpendicular to V. Okay. And if you take a look, if I want to go from this point right here, if I want to go from the initial to the terminal, my graph isn't 100%, but you'll notice, look at your signs. The negative tells me I've got to go left. The positive tells me I have to go up. So from here, if I went negative 1 half left and then 2.5 up, see, I'd end up at the terminal end of that vector I drew. Okay. Questions? Okay. Well, all right. Let's try one on our own. Okay, so given U equals 4, 2, and V equals 1, 2, first find the projection of U onto V. So the component form I want, W1, is the projection vector. Remember, it's that shadow. The formula was to take the dot product, divide it by the magnitude of what squared? V, and then multiply that by the vector V itself. Okay. So take about a minute. Let's see if we can find the component form of that shadow, the projected vector. Okay. And you'll notice I've actually already got U and V graphed over here. Okay. So U is 4, 2. So this one's U. 1, 2. This is V. I'm going to put this guy right here. All right. And then graphically, you can kind of confirm, is the answer you're getting makes sense with what we know about that shadow now. Okay, so let's see. Okay, so you may not be done, and that's okay, but let me go ahead and catch up to you. First, we need the dot product. So u dot v. Okay, so I'm going to multiply 4 times what? 1, so that'll give me 4. And then we're going to add the other product, so 2 times 2. So did everybody get a dot product of 8? Okay, good. Now let's find the squared magnitude. But if you're going to square the magnitude, that means you don't need to worry about the square root. Okay, they're just going to cancel. So all I'm going to have is a squared plus b squared. So for vector v, a is 1, so 1 squared is 1 squared. Okay, plus b squared, that would be 2 squared. So did everybody get 5 for the squared magnitude? Okay, remember those 2 items right there, that's the majority of your formula. Okay, all I need to do now is take the dot product divided by the squared magnitude and multiply it by v, which is 1, 2. And if I do that, what do I end up with? That would be 8/5 and 16/5. There you go. This right here, that's the vector projection. That's W1. What I'm about to show, that should be the shadow that U casts onto V. Okay. All right. So let's actually go ahead and do that. Let's see. If I were going to go ahead and cast U onto V, what I'm going to do, I'm going to go ahead and put my marker up to the screen. I'm going to go ahead and start to rotate. You tell me when to stop. Okay, now when you're telling me to stop is where you believe you should put the sun. So I'm going to go ahead and start here. Now remember, we want to go U onto V, so it wouldn't be above. It would actually be probably right about here. We always want to put U between V, the ground, and the sun, right?
Yeah.
Okay, so I'm probably going to be looking at something like that. That should represent W1. Okay, well, let's see. What is 8/5 as a decimal? 1 point what? 1.6? Okay. What is 16/5 as a decimal?
It's like 3.2.
3.2. So let's test it. Going from the origin to this point right here, and remember I'm doing this by hand, so is it okay if it's a little off? Yeah. Let's see. I would probably go this far right. Well, would you agree that's 1.6?
Yeah.
And then how high do I need to go?
3.2.
3.2, and it looks like I went a little above that. Okay. But I would say that we got it correct. How many people got the vector projection correct? Okay, good. Is it starting to make sense now as a whole with what it is we're trying to find? Okay. So now in B, what's it want me to do? There you go. That's just simply another way of asking what is W2. And the giveaway is that it gives the perpendicular, right? Okay. So graphically, where would I draw W2? There you go. I'd go ahead and connect the end of W1, the terminal, to U. Okay. And it should be perpendicular. That should end up being W2. Okay. Now, as far as finding him, that should be pretty easy. We know that U is equal to W1, the vector projection, plus W2, the perpendicular vector. So I could just go ahead and say that W2 equals U minus W1. I just went ahead and rearranged the formula. Okay. So what was U? Wasn't that 4,2? And we're going to go ahead and subtract W1, the vector projection that we just found to be 8/5 and 16/5. Okay. So we just have to do a little bit of algebra. This first one here, I'm going to need 4 minus 8/5. Excuse me. So I'm thinking 20/5. So 12/5. There we go. Because the common denominator would be 5. Now I need 2 and I'm going to subtract 16/5. So I'm going to change him to 2 over 1. What would be the equivalent fraction? Okay, so I'd end up with 10/5, and that would be negative 6/5. That should be the perpendicular component, W2. And I mean, just look at the signs. If I were to come back up here, because this was positive, that means I have to go right. And this is negative, that means I have to go down, correct? So if I'm going to come up here and look at my graph, to go from this initial to this terminal, didn't I have to go right and down? And those distances that we found should be how far I need to travel in order to get from the initial to the terminal. Questions? How are we doing? You guys have been really quiet today. Are we doing okay? It's close to Friday, so you just want to be done? I understand. I understand. I understand. There you go. Okay, well, there's only one other thing I'm going to go ahead and show you. Both of these types of word problems we were looking at yesterday, you can actually use the vector projection in order to get the same answers that we did, but I would probably recommend, whether it's a work problem or an incline problem, just continue to solve them the way that we did together. But I'm going to go ahead and show you step 2 now for work. I'm actually going to show you how the projection formula can give me the same answer. Okay. And if you like it, you can go ahead and use it. But again, I recommend just do what we did yesterday. Well, the only problem we did together was this one right here. Where was it? This one where we had a pulley system. We were trying to pull a container across the floor. And remember, all we did was take the dot product of the force vector and the distance vector, right? We ended up with 1,147.2 foot-pounds. Okay. Well, I want to go ahead and show you now how the vector projection formula could get me the exact same answer. Okay, so let me copy this down here. The force vector, it was 45.9, 65.5. The distance vector was it 25 feet? 25.0, okay. 25.0. Okay. All we did was multiply those two. We took the dot product. We got my answer, right? So what I'm going to show you now, if we go ahead and take the projection of vector F onto vector AB, the distance, if I take that, okay, and I multiply it by the distance vector, I'm going to get the exact same answer. Okay, but you'll notice I'm not using U and V, I'm using the vectors that we actually had in the problem. So let's actually use those variables to rewrite the formula. Okay, so the first thing I needed was the dot product, right? So I'm going to go ahead and take the force vector times the distance vector over. Now I'm going to take the squared magnitude of what? The force vector or the distance vector? The distance, okay? Because remember, the one that was being projected onto is the one that goes in the denominator. So I'm going to put the AB right here, and then I need to multiply that by vector AB. But this is simply the projection formula. That's what's required there. See, I would still need to now multiply it by the distance vector AB. Okay? Because remember, look at the parentheses. The parentheses is just the formula, and then I multiply it by the distance vector. Now, let's go ahead and plug in everything we know. We know that the force vector was 45.9. 45.9, whoops, 65.5 dot AB, so that would be 25.0, okay? Now, that right there just takes care of the numerator. Over. Now, we want to go ahead and find the squared magnitude of AB. So remember, that's A squared plus B squared, but wouldn't that just be 25 squared? Does anybody want me to go back and elaborate on that? Okay. times vector AB. So we've taken care of that. Now times vector AB. So times 25, 0. Okay. So this whole thing right here, that's simply the projection vector formula. So I still need to do what? I still need to multiply by the distance vector again. So 25, 0. Okay. Well, does anybody notice it? What's going to happen when I multiply these two vectors, 25, 0 times 25, 0? That's exactly right. Satish says it's going to cancel out the bottom. Because 25, 0 times 25, 0, well, isn't that the same as 25 squared? So those are going to cancel, and what do you notice we have left? Isn't that exactly what we did yesterday to find the answer? Okay. So see, that's why I'm not a big fan of the projection vector. Don't get me wrong, it's really useful, but it seems to me, didn't we kind of do extra work just so it would cancel out? And you still did the same thing we did yesterday. Okay, so that's why I encourage you just work those problems like I showed you yesterday. If you like the projection vector, please feel free to use it. I'm not going to go ahead and show you how to do that with the incline problems because it gets even more complicated. And I just want to make sure that everybody can do these. Okay. All right, so unless anybody has any questions, that is all I have for today. No questions? Okay. Then, let me pass out your homework. Now remember, when's this due? Tuesday. There's only 12 problems, so it's not a lot.
I can't.
Okay. And this will allow us to have the entire period tomorrow to work on the assignment. You can probably get it done within that time frame. Not have to worry about it at all until Tuesday. There we go. All right.